Okay, so let me move on to the discussion of expectation values and their relations, which will become useful later. And actually, to tell the truth, this is a bit complicated and makes me tired. So anyway, let me do this carefully. Okay, so here I'm going to define the expectation values of three different types of physical quantities. Okay, first, this is a state quantity. This is something we already know. A state quantity f takes value fj in a microscopic state j. And if you want to define the expectation value, you need to specify a probability distribution. And this is the definition of the expectation value. Okay, so it depends on p. This is something new and called a jump quantity. It takes value g, j to k, when a jump from j to k takes place. Okay, and here j and k are not the same. Okay, and for example, you can imagine that some amount of heat goes from the system to the heat bath when a jump takes place. Okay, so then, for example, this measures the amount of heat. And in order to define the expectation value of such a quantity, it's not enough to have only p, because we are discussing something related to jump. We also need to specify the set of transition rates, omega. And here's the natural definition. Okay, so here we first assume that the system is in state j. So this gives the probability that you are in j, and then there must be a jump from j to k. So we multiply this with this rate of the jump, and now we have j and k. So we multiply this with g and sum over all possible jk. Okay, and so this defines a good expectation value, and which depends p on p and omega. Okay, and since omega is the transition rate, so this defines the expectation value per unit time in certain sense. And I want to stress that because this is the expectation value per unit time, this is not a standard average. So I use this notation for the expectation value, but I would say this is a bad notation in the sense that if you take the expectation value of, say, 1, I don't know what 1 means, probably this is 1, of this, it's not 1. You get something like the escape rate or whatever. And as for this one, of course, this is a standard average. So if you average 1, you get 1. And I will discuss this from now on. But, even in this case, if you average 1, you get 1. Okay, so in this sense, these are standard expectation value, good average. But this one is not a standard average. And I will again say that this is a bad notation, but still useful notation. You see that this part was apparently inserted. Okay. Okay, finally, a path quantity. I think this is clear. A path quantity f double hat takes value f gamma in a path gamma. Okay, it's very similar to this one. Okay, so the state instead of state we have a path, and this is the expectation value, and it depends on the initial distribution and omega tilde, which is the whole set of transition rates. And I think the definition is obvious. So we know that this is the probability density for a path. So we multiply this with f gamma and sum over all possible paths. Okay, so this is our definition of path average. And here I used different notations for this path quantity. I used double hat and this whatever, double bracket or whatever, to define the expectation values. And the reason that I use this heavy notation will become clear in the next slide, in this slide. Okay, so suppose that we have a time-dependent state quantity f hat t. And here you can imagine that t is fixed. Okay, oops, sorry. Here you can imagine that t is fixed. And then this gives a state quantity, and so it takes value fj of t. Okay, now we want to consider this thing, which is the path quantity that corresponds to this state quantity. How do you define this? Well, this is almost trivial. We want to define the same thing as a function of a path. And so this thing, t is fixed. So this thing takes value in a path, I'm sorry, in a path gamma, this thing takes value like this. Okay. And gamma t is simply the path, where is it? Gamma t is defined here. Okay. Simply this is a state at time t. Okay. So, well, yeah, so this is almost obvious definition. Okay. So this is f gamma t. And now for some purpose, for some reason, I want to rewrite this in this form. This looks complicated, but it's essentially the same. And now I describe path in this way. So now I'm summing over this index 0 that, and so I'm looking at all possible states that the path visits. And here chi is the characteristic function, and it's 1 if inside is true, and it's 0 if inside is false. So actually, this is exactly equal to this thing. You simply pick up the state at time t. Okay, but anyway, for this state time-dependent state quantity, we have defined the corresponding path quantity, and a very important identity is this one. Okay, the left-hand side is the expectation value of this guy using the usual path average. Okay, so it depends on the initial distribution and omega tilde. And the right-hand side is the standard average, standard expectation value of this state quantity. So this is a very standard average expectation value like this, where P of PT or PJT is the solution of the master equation. Okay, so here on the left-hand side, we have a path description, and on the right-hand side, we have the master equation description. Okay, and this equality says that they are sort of equivalent. And of course, this is very natural and expected, but I'm going to tell just briefly remark how you prove this in page 46. Okay, so more important one is this uppercase F double hat. It's an integrated quantity. So now you integrate this F lowercase f double hat t over the whole time interval to get this quantity, total quantity. And this is a path quantity, and it takes value given by this. And so if you recall this or this, you find that this f gamma is given by this. And this is a very natural path quantity associated with a state quantity like this. You are simply integrating over all time interval, and you're just looking at the value of f at each time. Okay, and so we have this. This is just a definition, and if you take the expectation value of the both sides and using this, you see this identity. Okay. So the expectation value of this integrated quantity in the path average is equal to this. This is the standard simple average, and this is the solution of master equation. Okay, and this will be useful. Okay, now in page 45, we do similar thing for time-dependent jump quantity. So suppose that we have a time-dependent jump quantity g hat t. So again, suppose that t is fixed, and then this is when jump j to k takes place, it takes this value. Okay, and again we define the corresponding path quantity g double hat t with this. Now, I want you to recall this definition of this path quantity corresponding to f. In this case, we wanted to sum over all these, all the states visited by the path, and so we had this characteristic function here. But now we are taking care of a jump quantity. So now we need to only count the incidence of jumps. So whenever jump occurs, we can count it by using this delta function here, because jump takes place at t1, t2. So we sum over this jump quantity, the value of jump quantity, with times this delta function. Okay. Well, probably it's not very easy to understand this immediately, but probably yeah, later we look at this integrated quantity, and you will see that this is more natural. Okay, so so you will see the naturalness later. Anyway, we define this way, and then we have this nice identity. Okay, so the left-hand side is again the path average of this path dependent path quantity. Okay, time dependent path quantity, and this is the standard path average. And then I claim that this is exactly equal to the sort of simpler standard average of a jump quantity G. Okay, so this is a solution of the master equation, and this is just the transition rates at time t, and this is this jump quantity. Okay, again, I'm going to show this in page 46. So it's, yeah, this definition looks a bit weird because it includes delta function, but actually with this definition, we have this nice identity. Okay, good. So again, we can consider integrated quantity G uppercase G double hat and define like this, and then this takes value this, and now this is the integration of this. And as I said, now we can integrate delta function to get this. Now this is a very natural, good quantity to look at, isn't it? So this sums over all G's. I said that G can be like heat going from the system to the heat path. Then there are n jumps in this path, and this is just counting this is just counting the total amount of heat from the system to the path. Okay. Okay, so again, we can look at the expectation value of this, and then this is equal to this. So we have this. Again, the left-hand side is in terms of the path description. The right-hand side is more or less not much simpler description using the solution of the master equation. Okay, so finally, in page 46, I'm going to tell you how we derive these two relations. So this one in page 44 and this one in page 45. So let me start from this one. Okay, so we want to show that the path average of this thing, which takes this value, is equal to this standard average. It's actually simple. And to do this, we first rewrite this like this. Well, this is very trivial. If we simply inserted dummy index j and Kronecker delta. So this is just simple. But I recall that in page 41, we have shown this relation. What is this? Well, it's page 41. Let's go to page 41. I'm sorry, here. Yes, actually, this is a relation. Okay, so yeah, this is a probability density for a path and the sum over the path. So this one here is basically the expectation value of this Kronecker delta. The right-hand side is the expectation value of the Kronecker delta, and this claims that this expectation value is exactly equal to PJT, the solution of the master equation. Okay, so now we can go back to page 46. Yes. So this is what we have shown, and then we simply take the expectation value of this thing, and then we only have to consider the expectation value of this, and the expectation value of this is PJT, and of course this is simply this average. So we are done. Okay, this is easier, and in order to show the relation for G, we have to think a little bit, and now to show this, we first of all, integrate this over a very small interval. So delta t is a small quantity, and we integrate this expectation value in this time interval, okay? And then we look at this. So this takes value this, and we integrate this in a very small time interval, okay? And of course here we have a bunch of delta functions. And so if you integrate delta function, the result is either 0 or 1, right? And we get 1 if and only if one of Tm is in this time interval from t to t plus delta t, okay? And basically, if the time interval is very small, we can neglect the possibility that 2 of Tm's are in this time interval. So the integral of delta function is either 1 or 0. And when it is 1, we pick up this, and we further take the expectation value. Then what we get is this probability. So we are taking the expectation value of this 1 or 0 quantity, and the result is probability that there is a jump from j to k within this time interval. And we sum over possible jk, and well, yeah, this is here, okay? It was here. So this is exactly what we did, and okay, the remaining order delta t squared contains the contribution that there are 2 Tm's within this small interval, so on. Okay, now we look at this probability. So this is probability. This probability is that, I mean, to get this event, we have to, first of all, in the state j, and then there must be jump from j to k, okay? And within this time interval, the probability is basically this times this, okay? And this is this. And now, but if you look at this, this precisely gives this expectation value, and we have delta t here. Now what we want to do is to divide the both sides by delta t and take the limit where delta t goes to 0, and then the left-hand side becomes 0, and the right-hand the left-hand side becomes this, and the right-hand side becomes this. Okay, so we have proved the desired relations. Okay, I know that this is a bit confusing, and anyway, we did discuss this. So when we apply these relations later, please come back to these pages. Okay.